Okay, so we had two labs that were in the wave section, but one of them had to do with like using a Tupperware with water in it, some sponges for like waves, and then the other one had to do with sound waves and echoes, standing by a wall and trying to record the echoes. And it just doesn't seem feasible to do that, or even just to do that online with like a video. So I went ahead and we're gonna move forward with the next section. And the next section just has to do with light waves. So they're going to talk about first sound waves and light waves before they get into um, just kind of like more in depth with waves. So go ahead and pop open your How Light Travels HLT, How Light Travels 1.0 to 1.2. The first two parts of this are going to go by real fast. The second part's going to be a little bit more meat and potatoes, something for you to like really get into. So the document looks like this. This document will be graded. This document will be graded. So give you a moment to pop that up. So in the first section, we just have a quick little reading and states, sound and light both travel by waves. In order to hear sound or see waves, waves must travel from one place to another and either enter your eyes or enter your ears. How do you think these waves travel? One needs to travel through matter. So does light or sound travel through matter? B, neither one of them travel through matter, or C, they both need to travel through matter. So pick A, B, or C. And I think a good way to look at this, compare this, might be thinking about space, air, water, solids. And that might help you a little bit. So I'll give you a few seconds to, on the document, A, B, C, and then just kind of do your best. I know it's not probably easy for you to type explaining your thinking, but to the best of your ability, just go ahead and explain your reason for why you picked A, B, or C. And then I'm going to go ahead and just ask you A, B, or C. So do you think sound or light needs to travel through matter? Do you think sound or light does not travel through matter? Or do you think they both travel through matter? Okay. And then I think with the explain your thinking section, it's just going to be an idea of explaining why you think one of them, neither or both of them need to travel through matter. maybe just by putting an example. We're going to go ahead and move on to the next part. And again, this part's pretty fast, a little flimsy. Not much to it, but we'll still run through it. So the idea that they're trying to get you to come to mind is this: you are walking downtown. Maybe you're going to the conference center. Maybe you're going to a basketball game. Maybe you're walking from a parking spot or taking the light rail even to a baseball game, Chase Ballpark, or maybe you're going to what used to be known as Comic-Con. I don't know what they call it now. Or, just any one of those things that they have downtown. They have different plays, different events. Maybe you're going to the Orpheum Theater. Maybe you're going to go to City Hall. Any of those things downtown. As you're walking downtown, there's a lot of large buildings. So as you're passing through those buildings, and again, this little video that you're going to watch doesn't seem it's from the U.S., but the idea of a large city is still all the same. So as you're walking around, you see these large buildings, you need to use your other senses. And what do you hear is what the question's going to ask. So again, imagine you're standing on a busy street downtown looking up at skyscrapers. What do you think you are hearing? And this is just an 11-second video. We'll play it 4 or 5 times. So what do you think you're hearing? Maybe if you were traveling abroad, maybe somewhere in Europe. What do you think you would be hearing? And I'll give you about 40 seconds to type that in. And then we'll start taking some responses. Excellent. All right. In the public comments, public chat, we'll go ahead and just take volunteers. What sounds do you think can be heard as you're walking around downtown? Excellent. Those are all excellent. All excellent. I don't know how different it is. I mean, it's been years. It's been years. But they used to be like the first Fridays downtown. So maybe that could even be an idea. I haven't gone down to one in years. Cool, cool. So we hear a lot of talking about the cars honking, people talking, people laughing. Do you think the sounds that you would hear, let's say at the fair, would be different from the sounds that you hear that are downtown because of the buildings? Do you think the buildings have anything to do with any sort of sounds? And if the buildings do have anything to do with those sounds, um, what role do the buildings play? Like, let's say for just some reason your eyes were blindfolded or your sight was taken away temporarily. How would you know that you were in like a downtown rather than just like a busy place at like an outdoor mall? How would you know the difference between those two? Because again, you're listening. Okay, okay. But if you can't see the buildings, how would you know that the buildings are there? I'm really trying to like lead you somewhere in. Okay, okay, maybe you could bump into one, but by listening. I really appreciate you all kind of like playing along with this. How would you know by listening that there are sounds? Okay, I'm gonna give it another like 20 seconds. Okay. Um, the idea that I was trying to get to, and there's so much effort, and you're gonna be kind of like, oh yeah, when I tell you like what I was thinking of. But it's just the whole idea when you go to a place. Yeah, there you go, there you go, there you go. That's exactly what I was trying to like lead you towards. Um, when the sound bounces off the buildings, you hear like an echo. You hear like a very strong echo. And I always think of traffic, as many of you were saying. You hear the traffic, and you hear like a car honk. You can hear like bounce off the buildings and so forth. Especially if you've ever been to like um, a larger city, like New York. I mean, there's just constantly sound um, bouncing off, bouncing off the buildings and so forth. So that was the point I was trying to get to. So I mean, all of your other answers were outstanding. Um, so here is the oh, I didn't even assign it. Okay, I don't think it really matters that I assign it though. Here's the part that I really want to get into. So if light is the only electromagnetic wave that you can see, the rest of the how are the rest of the wave of the electromagnetic spectrum? How are they useful? We're going to find out. So here's a video. The video is also recorded and it's on YouTube for you to watch numerous times. And then what you're going to be doing on your document is just describing the waves and how are those waves being used. I do want you to make an effort to use the source material. I know that for some of it, you're going to have to perhaps go to the internet, but I really want you to refrain from just copying and pasting all these things down from the internet. Try to paraphrase it, say it in your own words, and try to use the source material, which is this video in McGraw-Hill. So we will watch this, and then you can watch as many times as you like. There is audio, and I did put subtitles on it like twice.
Visible light allows you to see the various colors on screen. However, light is just one small part of a broad range of waves called the electromagnetic spectrum. At one end of the spectrum are waves that have long wavelengths, low frequency, and are low in energy. At the other end are waves that have short wavelengths, high frequencies, and are high in energy. Along with visible light, we classify these waves into several types. Radio waves are used for communication. They have wavelengths that range from 30 centimeters to a kilometer or more. The microwaves you use in a microwave oven to cook food have wavelengths between 1 millimeter and 30 centimeters, so they have fairly low frequency and energy. A TV remote control often uses infrared waves to send commands. Their wavelengths are shorter than microwaves, but longer than visible light. On the other side of visible light are ultraviolet waves. UV waves have a shorter wavelength than visible light, so they have higher frequency and higher energy than visible light. UV waves can cause chemical reactions that can lead to cell damage. Concentrated UVC waves are used to sterilize medical equipment by altering or killing organisms. The waves with the next highest energy are X-rays. These short wavelength, high frequency, high energy waves are used in medical imaging because they can easily travel through soft tissue. The last classification of electromagnetic waves are gamma rays. They have the shortest wavelength, highest frequency, and highest energy of the electromagnetic spectrum. They can kill cells and are used in cancer treatment. All of these waves make up the electromagnetic spectrum.
So I'll kind of leave it right there for a few seconds. Go through this and, with a little bit of qualitative, quantitative descriptions, just trying to put some description on each part of the electromagnetic spectrum. So this one's talking about the actual wave itself. And in the red, it's talking about the characteristics or the uses. So what do we use all these different waves? The bottom one here is just kind of a little bit more of a silly, just a friendly wave. Just to be a little bit unorthodox. But again, these are talking about the wave itself. Does it have a high frequency, low frequency? Is the wavelength? Yeah, the link to the video is actually right here, but I'll put it in the I'll put it in the chat for your convenience.